Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we're going to work on how to determine the real zeros of polynomials. Now, it's really the real rational zeros of polynomials, but I wanted to make the title a little bit shorter, so that's why I would just simplify it to real zeros. But we're only going to focus on rational zeros, and we're not going to look at the graph like we did in the first lesson in this chapter of polynomials, but we're just going to look at factoring, how to find the real zeros via factoring, and that's going to basically be our main purpose. So what we're going to cover in this lesson is, how to find the real zeros by factoring, as well as how to write the equation when given real rational zeros and their multiplicity. All right, so that's basically the two ideas that we're going to cover. Now, to go over this, we're going to go through we need to review some of our definitions. We're not going to be introducing anything really new, but I did want to kind of provide some additional definitions, or just kind of go back through the definitions that we've already talked about, throughout the course so far. I also wanted to let you know that I kind of did a little work ahead of time. Usually a lot of times, the purpose of these videos is for me to kind of go through the notes, so therefore I can fill in the rest of the notes so it's available. But what I did is I also just spent a little time instead of recording it, just to kind of provide the notes that my students already have. So therefore I can just add on to that. So the first thing is just understanding the zero product property. Remember, when you have a product equal to zero, then one or both of those products have to equal zero. In this case, obviously 5 is not equal to zero. So then A has to equal zero. Here, we don't know what A and B are, so therefore either A is 0 or B is 0, or they're both 0. So it can be just like with one number, or one variable, two variables, or it could also be with expressions. Like if I had the expression x minus A times x minus B, then either this expression equals 0 or that expression equals 0. So that's what the zero product property tells us. And again, the idea of looking for is a product equal to 0. And that's what we've already kind of discussed so far in that linear factorization form, which again, I'll review again. But again, when we have a product equal to 0, what we're doing is that allows us now to apply the zero product property. And that's what we're looking for when we're finding the real zeros, or really when we're finding any zeros of a polynomial. We're looking for when f of x is equal to 0. So if you have a function in function notation, if we want to find the zeros, you're going to replace f of x with 0. If you have a function in y equals notation, then you're just going to replace y is equal to 0. And this is something that you are familiar with. In quadratics, we might have said find the roots, or find the solutions, or find the x-intercepts. Now we're just really using the vocabulary of the zeros. And again, today we're only going to focus on the real zeros. But again, if you can see that since this is already in factored form, now I can go ahead and apply the zero product property. So that's the nice thing about having factored form. When you have a product equal to 0, you can apply the zero product property. And obviously we know that not everything is always in factored form. That's why we're going to practice factoring in this case. And then we just wanted to get through the multiplicity. This is something we covered again in the first chapter. Just making sure that you obviously, when you see, or obviously understand that when you have, I should probably add this. When you have an equation in factored form, right? And did I write the linear factor? So here is the factored form of this. You can set each and every one of these equal to 0 and find, hopefully we remember from this, we can easily identify what the zeros are as well as multiplicity is. If you don't understand the multiplicity as the behavior of the zeros, you can also just think of them as odd or even if they're going to cross or if they're going to bounce at each and every x-intercept. And then just also remembering, how I figured this out so quickly was obviously we already covered this in lesson 1, but also just understanding the linear factorization. When we have a polynomial written as a product of its factor, we call that the linear factorization. And that's really helpful because, if you have something in this format, you can easily just list the zeros as C1, C2, and C3, right? That's why I didn't even have to apply the zero product property. I mean, you could have, right? I mean, you could have set each and every one of these equal to 0, but you can see, if you set each and every one of these equal to 0, you already know, divide by 2, x equals 0. If I have, x minus 1 squared is equal to 0, well, you're first going to take the square root of both sides, x minus 1 equals 0, and then x equal to 1. So if you kept on doing that, you would still get the same exact answer. So that's what's nice about understanding things in the linear factorized form. As long as there is linear factors, you can quickly and easily identify the linear factors. A couple key points. linear factors is a product of your factors. So if you have like a +5 or a minus or anything at the end, those are not in factored form. So these two, are not linear factors. So we got to make sure it's only a product of your factors. Also note that sometimes, we don't have everything written as x minus c. Like for instance, a lot of times if it's just an x, we just leave it as x. We don't write it as x minus 0. But that really is what the 0 is, right? It's, when x is equal to 0, that makes a 0. So we don't really write it in this form. But obviously it's important for you to understand that exactly is, that is the idea. You could do that. There's nothing wrong with that. And then also the other important thing that, again, I just have to keep on reminding students, 2 is not a 0, right? We know that this is a line. There's only one x-intercept here, which is at 1. So that is your linear factor. 2 is not a factor. It is a scalar. And again, if you were to set this equal to 0 and solve, the first thing you do would be divide by 2, and therefore you just still have 0 equals x minus 1. So you can see the only answer is x is equal to 1. 2 is not a factor there. All right. So then what we did is we kind of started the lesson with actually factoring or defining the zeros in the multiplicity. So I gave this to all the students and I said, all right, let's just go ahead and find the zeros in the multiplicity. I have, I think, 5 groups in my classroom, so nobody really got to do A, but A is pretty easy. Like that's already kind of what I looked at. If you already have this in factored form, you replace f(x) with 0, and then you apply the 0 product property, and you solve, and then you can just list the multiplicity underneath, right? Now you can see B is not in factored form. So there's nothing really, we can't use inverse operations because we have 2 x's, right? If it was a linear, if it was like a line, you could just use inverse operations, subtract the 4 and do some things. But in this case, this is a quadratic. We can't use inverse operations. So we're gonna need to factor this. So fortunately, this is something that we already know what the factored form is. It's an A. Okay, so what 2 numbers, multiply to give you 4, add to give you -5, that's -4 and -1. And if you multiplied that out, you would get that polynomial. But the purpose that I wanted to see with this second step is to understand the importance of when finding the zeros, when you have this quadratic or more than one x, using factoring, setting this up as a factor, as a product of factors. Therefore, then you can apply the 0 product property. And again, you're going to get the same answer. It's just the same equation represented in 2 different situations. So obviously, a lot of the time, in day 1 of this lesson, we only left with product of factors, just so you can get used to identifying the zeros from a product of factors. Well, now we're going to looking at polynomials in this non-factored form, in the standard form. So therefore, to finish this, to find those zeros, we're going to have to practice factoring. And obviously this is a quadratic, so this is not really something incumbent in our class. We're going to get into more advanced polynomials, which we'll kind of continue working on. So the first kind of step that I told students, or that I wanted students to recognize is first, if they have a common factor, right? If they share a common x or they share a common number, factor that out. So immediately a lot of times students will look at this problem and say, oh, it's raised to the 3rd power. I don't know what to do. I know how to factor a quadratic. I don't know how to factor a cubic. Well, if you look at, once you factor out the x squared, which is like dividing out the x, right? And again, you're rewriting this as a multiplication problem. That's all factoring is. If you want to multiply that x back in, you'd see you're going to get the original problem. So by factoring out the x, you see inside the parentheses down, we're back to our original problem again. And now I can just factor that down really easily. And now I just notice I have 3 zeros, right? Which would make sense because this is to the 3rd power, 3 real zeros. And therefore, my zeros are just 0, 4, and 1. And then I also introduce set notation. So rather than listing out all the zeros, sometimes we're going to have like a lot of zeros. So it might be easier just to list the zeros in in terms of a set. And if they're inside the set and there's no multiplicity there, then I will just assume that the multiplicity is going to be 1. All right, so for D, this is where we start to have to kind of make this mental jump, all right? And so, a lot of students do not like when it's raised to the 4th power, which I understand. It's not something that is, something that obviously makes a lot of sense to them. But the main thing I wanted students to come into, all 6 of these problems, sorry, not that one. Well, let's just look at these trinomials. B, C, D, and E. They all have the same numbers as far as coefficients, -5 and +4. So I think we can all agree, if we are going to factor a trinomial, like one thing we have recognized from factoring trinomials is they produce a product of 2 binomials. So I'm not sure, let's pretend I have no idea how to factor this. But I do know that if this is a trinomial, I can factor it down to a product of two binomials. So that's basically what I do. I just write up two binomials. Just like this problem, and this is really what I just want to relate this to. Like these have to be the same, okay? You know, the -5, they both have -5, they both have a +4. So I know the numbers inside these product two binomials is going to be -4 and -1, right? And they also, instead of x times x here gives me x squared, I need this x times x to give me x to the 4th. So all I'm going to do is raise the power of my factors. And again, we can do this for like any product. Like for instance, what if I gave you x to the 6th minus 5x cubed plus 4? Well, I know that's going to be factored down into an x minus 4 times x minus 1, right? Like that does not change, right? We know that those numbers have to be the same. But instead of x times x giving me, like when I multiply this, x times x gives me x squared. I don't want it to give me x squared. I need it to multiply to give me x to the 6th. And when I combine my like terms, I don't need 5x. I need negative 5x cubed. So all I'm going to simply do in this case is just raise the power to the, raise it to the 3rd power. Okay, so that's basically, you know, that same idea and that same process and that same mind shift that I want students to kind of take. Now, you can see we keep on getting higher and higher, right? We're getting to the 5th, we're getting to the 6th. So it starts to kind of get a little bit more confusing. But again, if you just kind of think about this and say, all right, let me identify what I can factor out first and then see how I can factor it down. So in this case, you see they all share an x, so I factor out the x. And then I recognize, oh, this is x to the 4th minus a 5x squared. Okay, I can do a problem like this. This is just like the one I did over here. So I factor out and actually I'm not done with this one. Hold on, I got ahead of myself. So anyways, I get this to an x squared minus 4 times x squared minus 1. But again, be careful. Don't say the zeros are 4 and -1. That's a very other common misconception students will make here, is because these are not in linear factored form, right? This is x squared and x squared. So if it's a linear factorization, x needs to be to the 1st power. So I recognize I can factor these down by difference of two squares to be x minus 2, x plus 2, x minus 1 to x plus 1. Therefore, using the zero product property and finding my zeros, I get my zeros to be plus or minus 1 and plus or minus 2. On to the next one. So on the next one, you know, kind of in that same idea here, we're factoring out the x first. Even though it's raised to the 5th power, and you're like, I don't know how to factor something to the 5th power. Well, when you factor out the x, again, you get back to this original problem. So I'm not going to go ahead and rewrite the linear factorization. You can also just think about this as you can set each of these factors equal to 0, right? You could figure out the plus or minus 2 and the 1. Oops, sorry, that's supposed to be squared. So you can, again, figure out these zeros as long as you remember it has to be that plus or minus, right? If you were to use a zero product property and not write the linear factorization, then you could go ahead and figure out, as long as you figure out the zeros. But a lot of students will, you know, make that mistake and they will only do 4 or they'll only do +2. They won't do the plus or minus because just remember, if you were to use the zero product property here, this becomes x squared equal to 4. So x is equal to plus or minus 2, right? Not just +2. So that's why, you know, either show the work of applying the zero product property or write out the linear factorization. All right, and the last one looks like the most complicated at all. You know, 2x to the 6th, like what am I gonna do here? But again, if you just train your idea to factor out the GCF first, you factor out x squared and you say, oh, this is back to that, you know, original problem. Like I can easily factor that out. X minus 4 times x minus 1. So obviously we know the zeros here are 4 and 1. The issue, though, that comes with this one is people see this 2x to the 4th, and again, they want to attribute 2 to be a 0, which is not a 0. It's a scalar. And again, if you were to solve for x using inverse operations, you divide by 2 on both sides. You get x to the 4th equals 0. Then you take the 4th root on both sides, and you get x is equal to 0. However, it has a multiplicity of 4, and you can see that's where we're going to get that's where that comes into play. So, you know, it's just very important to understand the difference between a factor and a scalar. And then also, since this is in set notation, I'm going to put the multiplicity of 0. Since it's not 1, I'm going to write that in separately. All right. And then the These are examples actually I wanted to go through in the class, but we just didn't have time. So I'm going to just kind of run through it with you. Here's basically 4 problems. They're all actually the exact same problem. They're just written in different forms. Okay. And, or they just kind of start in different forms. Here, it's written as a linear factorization. So again, when you set this equal to 0 to find the zeros, you can just apply zero product property, and then you can list them as +1, -1, and -2. You could also probably just find the zeros just by looking at them, right? The next one is, again, when you are, or I'm sorry, so first one, then the main important thing is writing the linear factorization. So that's already written as linear factorization. So there's nothing I really need to do. This one, though, is not written as a linear factorization. So you don't need to find the linear factorization to solve, right? You could easily set each factor, since we're basically, finding the zeros. You set this polynomial equal to 0, and I have 2 of them, so I can set each and every factor equal to 0. Go ahead and solve. When I take the square root of both sides, you can see I get x equals +or -1. And again, I cannot break down again how important it is to do plus or -1 when you're taking the square root. However, this is not the linear factorization. So if I do ask for the linear factorization, make sure you factor out this x squared minus 1 to x minus 1, x plus 1. And again, that shows and proves that we have that plus or minus is there. So you can either look at the plus or minus by the linear factorization, or by making sure that when you introduce the square root, you're using plus or minus. Now, the next example is an odd way that a polynomial would be presented to you, but it's really, the only reason I'm really presenting it is therefore you can make the jump into our next factoring technique, which is factoring by grouping. So in this case, you can see that we have a product here minus another factor. So it's kind of weird. It's not in linear factorized form. And again, we want to always look into factoring out the GCF, what any terms, quantities have in common. You can see that this front, this expression and this expression both share x plus 2. So if I factor out the x plus 2, I'm just going to be left with an x squared, and then you could say -1 right there. Okay, so they share an x plus 2, you factor that out, and now by factoring out the x plus 2, I've rewritten this as a product of 2 factors, right? Which again, now to fall to zeros, I can write the linear factorization, and therefore I can quickly and easily find the zeros. So this is the important thing, is doing it this way so that you can just understand when we're finding the zeros, as long as it's not a line, we're going to need to look to factoring more often than not to be able to solve. Okay, so don't try to use inverse operations when you have multiple variables of x, x to the different powers to try to solve. So then that comes into that grouping technique, which is, for our answer, is when we have 4 terms. So I think we are pretty comfortable, or at least hopefully we get pretty comfortable with factoring trinomials when they are factoring, trinomials. Doesn't matter if it's to the 2nd power or to the 5th power or to the 6th power, I'm sorry. We see that, we factor them into a product of 2 binomials. So is that the same case when we have 4 terms? Is it factored to 2 binomials? And no, we have to use a different factoring process, which is grouping. Now, so grouping, all we're simply going to do is group the first 2 terms and group the second 2 terms. You got to be careful when you group the second 2 terms with the negative to make sure that you just don't put a negative or grouping symbols on the outside, right? If you put, for instance, if I have -x minus 2, that is not the same thing as -x minus 2. You just can't put parentheses around -x minus 2. However, that is the same thing as -x plus 2. So when you're going to put grouping symbols around those last 2 terms and you have a negative, just make sure you change the signs, because again, when you distribute that negative, right, that's going to give you -x minus 2, when you multiply that negative through. So that's exactly what I did. I grouped the first 2 terms, which was positive, so it was fine. And then when I grouped the second 2 terms, I just changed the sign. Then all you're simply going to be doing is factoring out the common terms, like factoring out the GCF. Now, in this case, we have x squared plus 2x, so therefore we can factor out an x squared, and that's going to leave us with an x plus 2. Now, in the second case, I don't need to factor anything out. You can see that they already have common terms in common. Now, again, the important thing or nice thing about this is this is now just like the last problem we did, right? You can see how they both share that x plus 2. So now I can factor that out. And by factoring that out, I didn't write the linear factorization, so let's go ahead and do that, because I never did that. So that's going to be x plus 2 times x minus 1 times x plus 1. Okay, so that's the linear factorization of a polynomial that's in the standard form. Okay, so that is our factoring practice with 4 terms, which we'll obviously do some more examples on. So really for my students, I just broke it down into three kind of ideas. The process of when you have 2 terms, look to factor just out a GCF and or also look to factor using the difference of 2 squares. If you are factoring with 3 terms, look to obviously factor out the common terms first, and then just look to factor like a quadratic trinomial. Okay, so maybe I'll put parentheses like factor it like a quadratic trinomial. If 4 terms, then look to factor out the common terms, obviously, and then look to factor by grouping. Okay. Oh, did I forget to do these? I forgot to show the rest of these. Oh, I thought I did the rest of these. Oops. Okay. Well, so these are the examples I did in class. I actually meant to finish these problems, but I guess I got distracted and didn't finish them. So in the first example, though, you can see I factor out the 4x cubed because that was the common factor. And then therefore I have this times this, right? And again, so I have a product of 2 factors equal to 0. So I can set each factor equal to 0. Go ahead and solve using my inverse operations. I get x equal to 0 with a multiplicity of 3. Subtract 1, divide by -5. I get x equal to 1/5 with a multiplicity of 1. So therefore you can see I just listed the zeros as 0 with the multiplicity of 3 and then 1/5. So I guess maybe this would be good for me to go through this as well. Now the fun thing about this, the fun thing about this is a quadratic trinomial when a is not equal to 1. So however, if we're thinking about the same process that we've done before, we know that this is going to factor into a product of 2 binomials, right? We know whatever's going to multiply to give us our first 2 terms and our last 2 terms. Now, actually, before I get to that case, let's factor out common terms, right? And we see that they all share an x squared. So if I factor out an x squared first, I should have talked about that first. Then I'm going to get a plus a 4x plus 1. Okay. So now I know that's going to be 1 factor x squared, right? That's going to be a 0. That's going to have a x-intercept or a 0 of 0 with a multiplicity of 2. But now I need to factor this down. Now, hopefully we're pretty familiar with factoring when a is equal to 1. But what do we do when a is not equal to 1? Well, one thing I, again, tell my students is we know this is a trinomial, right? It's a quadratic trinomial. So we know it can be broken down into a product of 2 binomials. Okay, so now we just got to think, well, what 2 numbers multiply to give us, 4x squared and then 1? Well, we could easily do just a 4x and an x and plus 1 and plus 1, right? Majority of the time in this class or in other classes, majority of the times your problems are going to be relatively simple. So, a lot of times until you get good at this, just use guess and check. Let's just pick. We know 4 times x or 4x times x gives us 4x squared and 1 times 1 gives us 1, right? So now we just need to make sure, do our middle terms give us 5x? And you can see that, middle terms give us 4x. Well, no, 1 times x is 1x. 4x times 1 is 4x. 4x plus 1x is 5x. So we need to get to 4x. So again, it doesn't matter if I change this to -1 and -1. That is not going to work, okay? So that is not going to be our factored form. Let me just put this in f of x form. So let's go ahead and try it again. So I don't think 4x and x are going to work, so let's go ahead and try 2x. And what do you know? 2x times 2x is 4x squared. 1 times 1 is 1. This gives you 2x, and that gives you 2x. 2x plus 2x is 4x, so that works. Now again, oops, why did I put not equals? Now again, the important thing to recognize here is I can actually simplify this, right? I can actually write this as, that's an x squared, of 2x plus 1 squared, right? Because it's a binomial times a binomial. So you can see actually in this case, this is written now in a simplified form. Hopefully you can our zeros now are going to be 0. You could set each one of these equal to 0 and solve. So hopefully you recognize that's going to be 0 with a multiplicity of 2. And this would be a -1/2 with a multiplicity equal to 2. All right. And then the second example I did here, kind of doing the exact same case. If I wanted to rewrite this. Now, in this case, when you're dealing with the first term, I can just factor out, group this like this, and then group it like that. All right. So factor out the GCF here. Let's just factor out a x squared. So if I factor out a x squared, that's going to leave me with a -x plus 2. Now, the important thing here is I want this, remember, if you look back into the last example, I want these products to be exactly the same, right? So I could factor out a 9. Like, there's nothing wrong with factoring out a 9. The only problem is if I factor out a 9, I'm going to get an x minus 2. I don't want to get an x minus 2, right? These are not the same anymore. So I don't want to factor it out that way. I'm still going to factor out the x squared to give me negative x plus 2. Or you could factor out a negative x squared. That would satisfy that as well. Or the other way we can just break this down is why don't we factor out a negative 9, and then that's going to give us a negative x plus 2. Now you can see that those are exactly the same. So now I can factor those out. So now I set this equal to 0, right? Because we're, again, finding the zeros. And now that's going to give me a negative x plus 2 times a x squared minus 9. Okay, now I have the product equal to 0. Now I can apply the zero product property, or to write this as a linear factorization. And if I wanted to write this as a linear factorization, I could factor out a negative to give me x minus 2. This can factor down via the difference of two squares. Okay, and therefore you can see they all have a multiplicity of 1. So therefore I would just list my zeros as 2 and plus or minus 3. Okay, so those are the 3 examples I went into the class. And then I wanted to kind of discuss more these examples here with you. So let's go and look at 4 more examples just to really kind of practice what we're working on. The first example, it's fairly basic. Let's just go ahead and replace this with 0. Again, we're just going to look into factoring this as a quadratic, right? Because we see that it's a trinomial. So I just like to a lot of times think of it like this. Like, what is the factored form of that? Well, the factored form of that, hopefully what 2 numbers multiply to give you 1, add to give you negative 2, that's going to be x minus 1 times x minus 1. So this is going to have the same factors. The numbers aren't changed. The only difference is we need this to multiply to give us a x to the 4th. So therefore, that's going to be x squared times x squared. And again, if you're not sure about this, I'm sorry, that should be, yeah. If you're not sure about this, then multiply it out, right? Multiply that out and you'll see that it does, in fact, give us that binomial. Now, this is a binomial squared, so we could write this as x squared minus 1 squared, but I think that kind of gets a little confusing. So the best thing I would recommend is, and what did I ask? Did I ask to write the linear factorization? I didn't. I should have done it. Find all the zeros of the polynomial and label the multiplicity of each. Okay, well, I'll just practice writing the linear factorization, because I think writing the linear factorization here, even though you could solve these, if you do the zero product property, you might not obviously see what's going on here. But if I do the linear factorization, watch what happens. X minus 1 times x plus 1, right? Difference of 2 squares. X minus 1 times x plus 1, difference of 2 squares. So what you see here is we actually have some repeated factors. So therefore, we actually are going to use our multiplicity in this case. This really can be rearranged to x minus 1 squared and x plus 1 squared. So therefore, my zeros here are going to be plus or minus 1, both with a multiplicity of 2. Okay? And sometimes a lot of you wouldn't have seen that if you just would have set those equal to 0. But if you would have set them equal to 0, you would have x equals plus or minus 1, and then x equals plus or minus 1. But you need to understand that those would have been repeated. And you can't have double x-intercepts, right? So what happens when you have repeated zeros or repeated x-intercepts, that changes the behavior of them. And that's what we obviously get with the multiplicity. For the next example here, let's go ahead and set this equal to 0. I recognize that I can factor out an x squared. Okay, so that's good. And by factoring x squared, I'm left with a 2x squared minus x minus 3. And crap, I have another quadratic trinomial where a is not equal to 1. But again, I know it can be factored down to a product of 2 binomials, right? So let's go and figure out, well, what 2 numbers multiply to give me 2x squared? Well, that's going to be 2x and a 2x, right? And what 2 numbers multiply to give me negative 3? Well, guys, we only have so many options. Negative 3 and positive 1, and positive 3 and negative 1, right? Oops, I'm sorry, that's not an x. That's just supposed to be an x. So from here, we're just going to go ahead and look at and say, I need where should the 3 go, and where should the 3 and the 1 go, and which one should be negative? And in reality, just pick a spot and then see if it works. Now, I automatically know if I put a 3 here, it doesn't matter if it's positive or a negative, that's going to give me 6. And this other term is going to be a 1 times x. Well, the difference of 6 and 1 is 5. And I'm not looking for 5. I'm looking for a difference of 1. So what I'm going to want to do is I'm actually going to want to put the 1 over here. And I'm going to want that to be a positive 1 because I know that 2x times 1 is less than negative 3 times x. And again, if you think about combining these middle terms here, like 2x times 1 is a positive 2x, negative 3 times x is a negative 3x. Negative 3x plus positive 2x is a negative x, and you can see that's your middle term. So now, hopefully you recognize that from there, that's in our linear factorized form. So therefore, we can pull out these zeros to be a 0. Oops, I'm sorry. Yeah, 0 with a multiplicity of 2. Make sure you include the multiplicity. And you could write that like, do linear factors. Could you write this as x times x? You could. But again, remember, I just kind of think of x squared as x minus 0 squared, right? We just don't write the x minus 0 from there. So therefore, that's fine as far as a product of linear factors because the 2 represents the multiplicity, not the power. So x equals 0 with the multiplicity of 2. Then we're going to have 3 halves. Again, if you were just to set these equal to 0, plus 3, 2x is equal to 3, divide by 2, x equals 3 halves. And then also x is equal to negative 1. Okay, moving on to the next example. We have, again, factoring by grouping. So in this case, I am just going to rewrite this by grouping terms. So I'll have 0 equals x cubed minus x squared. Now again, I'm going to factor this. I want to group these second 2 terms, but since this negative's there, I'm going to change the sign, right? And it's very important to change the sign. If you don't change the sign, then what you're doing is you're changing the problem, right? Because negative times 4x is negative 4x, and a negative times a negative 4 is a positive 4. So now I can factor out the GCF of each of these terms. In this case, I have an x squared. So that's going to give me an x minus 1. And in this case, to get a x minus 1, I'm just going to factor out a 4. So I already have the negative there, so factor out the 4. And that's going to give me an x minus 1. Now, these are exactly the same, so I'll factor that out. X minus 1 times a x squared minus 4. You could solve from here. Just make sure you do that plus or minus. Or you could go ahead and write the linear factorization, x minus 1 times x minus 2 times x plus 2. And you can see they all have a multiplicity of 1. So therefore, I'm going to have 1, comma, plus or minus 2. All right, and then into our last example here. Again, doing the same thing, or I'll go ahead and work on completing the same thing, is set this equal to 0. To x cubed plus a 6x squared. Group those 2 terms. Group this term, but change the sign. All right, here I can factor out a 2 to x squared, sorry. Okay, by factoring out a 2x squared, that's going to leave me with a x plus 3. And then here to get an x plus 3, I'll just factor out a 2. So that would give me an x plus 3. Now I can factor out the 3, or the x plus 3, I'm sorry. And that's going to leave me with a 2x squared minus 2. Now, again, from here, you could factor this out, but let's factor out the 2 again. So let's actually rearrange this. So if I factor out the 2, that's going to leave me with an x squared minus 1 times an x plus 3. Okay? Now, in this case, you could do the linear factorization. But again, if you kind of struggle with the linear factorization, you're not good at factoring still, you can just go to the zero product property from here. Just remember, we're not going to set that 2 there because 2 is not a factor. It's a scalar, right? You would divide by 2 out. First thing you would do there. So therefore, you would get, x equals plus or minus 1, and x is equal to negative 3. So the zeros in this case So the zeros are going to be plus or minus 1 and negative 3. All right? So that is basically what we work into with the factoring form. You can see the work that we did, like the factoring, either if it's 3 terms, 4 terms, 2 terms, but basically we're doing the same factoring process we've really learned before, factoring out the GCF or factoring trinomials into binomials. We're just kind of changing the problems, working into some higher powers. But the understanding, again, that, it's really important is we are given a polynomial. We wrote the polynomial in factored form via factoring. Then once it was in factored form, we set it equal to 0 to find the zeros, because that's the definition of finding the zeros. We could set each and every factor equal to 0 via the zero product property, and then we solve to find the zeros. And so, therefore, in our next example, we're going to want to write the equation, which is basically like the exact opposite. If we're given the zeros, to work backwards to write the polynomial, we have to take the zeros, we have to find the factors, and then we have to multiply them to get our polynomial. So to kind of like explain that point, what I did is I just kind of worked through some equations here, and I said, write the equation of the polynomial. So we kind of worked, these are all the exact same problems. But again, just kind of show my steps here is, what if I gave you f of x equals x minus 2 squared, 3x plus 1? What if I gave it to you in factored form, and I said, write the equation in standard form? Well, then you just need to multiply everything out. So you need to multiply x minus 2 squared, which when you multiply via distributive property gives you x squared minus 4x plus 4, right? Well, then that needs to be multiplied by, let me write that up there in case people didn't understand what I was doing. X squared minus 4x plus 4 would then need to be multiplied by 3x plus 1. Now, you could do this via distributive property again, but I taught my students to use the box method, typically when you're multiplying with trinomials. The nice thing about the box method is, again, the diagonals combine to give you like terms, so that was nice. And it's just a little bit easier, a little bit smoother. All you're doing is, when you're multiplying two terms or two quantities, that's basically giving you the area. And you can create columns and rows based on how many terms you have. And basically you just find the area of each little box based on with those terms. And it's kind of easy to like combine like terms, and therefore you can see there is our final polynomial. So if you have it written in factored form, to write the polynomial, you just multiply out. Here, we have this written as a linear factorization, right? Here is x minus 2 squared, so it's just important to understand, if I have x minus 2 times x minus 2, that's x minus 2 squared. And then I would just multiply all, I would actually expand that out to give you, again, our original problem. Or what if a problem I said, just here are the factors, right? I didn't give you a polynomial, I just said, here's the factors. So intuitively, we need to understand, if you're given the factors, then we know that the product of the factors gives us our polynomial, right? So we just take those factors, write them as a product, and obviously I didn't do the math every single time because obviously it's just redundant. But you can see how I wrote this when given the factors. Now, the important skill set or thing to understand is, what about if I gave you the zeros? What if I gave you a 0 of 2 and negative 1/3? Like, how would we write the polynomial from there? Well, again, remember from our solving problems. Like when we have the zeros, we can write the zeros in set notation. We could also write the zeros just as x equals 2 and x equals negative 1/3, right? And again, where did we get the zeros? Well, they were set equal to 0 via the zero product property. So when I had this equation and I wanted to find the zeros, I solve for x. So working backwards, I can take both of these and set them equal to 0. Now, the interesting one is this fraction, because the easy way to do this would just be to, multiply the 1/3 over. However, if you notice, if you were to multiply x plus 1/3, then you would have fractional coefficients. And typically in polynomials, we want to avoid fractional coefficients. And I think for any of you out there, doing this, you don't want to multiply, you don't want to like simplify with fractions, right? It's not going to be fun. It's going to make the problem more difficult. So rather than just simply adding the 1/3, what we can do is just apply our inverse operations. Multiply the 3 on both sides and then add the 1. And then when you have these quantities equal to 0, we recognize that those are the factors of the polynomial, right? That's a factor and that was a factor. And you can see how they come into there. Now, the important thing also is it could be a 2 could be there, a 3 could have been there, a 12 could have been there, a 22 could have been there. It doesn't really matter what that scalar was. That did not impact my zeros. So that number is like an arbitrary, it could have been anything. That does impact the graph, but it does not impact the zeros. And that's something very important to get to. Because when I work through my examples, we'll see how that kind of comes into play. And so therefore we get the zeros, then we get the factors, and factors equal 0, and then you multiply them. Okay, so basically the process for writing the equation is fairly simple. You just write each zero in factored form. If we're given the multiplicity, you apply the multiplicity to each factor, and then you expand multiplication and simplify. And that's basically kind of it. Now, obviously, there's some variations. That's a very simplified version of this. And what we're looking for is, for example, like what if I want a leading coefficient to be a number? Or what if I want a point to be on the line, right? Because again, remember, this represents a coordinate point. Negative 1, 2 has to lie in the polynomial. So let's kind of look at this first example and see how that changes things. So here I have my zeros. So I set them all equal to x, okay? And then I set them equal to 0 to find the factors, right? So there's a factor, and there's a factor. So therefore, I write them as a quantity, a product of each factors, remembering, not forgetting that x plus 3, this x plus 3 has a multiplicity of 2, so I need to raise that to the power. Then you need to expand that. Hopefully you could use box method or distributive property, or hopefully start working on these in your head. Just remember, x plus 3 squared is not x squared plus 9, right? You got to actually multiply it out, x plus 3 times x plus 3. Here again, I multiplied this in my head, doing this just because I do so many of these, but I hope that you guys could eventually kind of get to that point. However, multiplying a trinomial times a trinomial, I did not want to do in my head, nor did I really want to like work it all out, and do lines and all that kind of stuff. I think it's just going to be too confusing. So therefore, that's why I reverted to the box method. And you can see again that via the box method, my terms on the diagonal are all like terms. Right? Those are all x squared, so you can combine them. Those are all x's, so you can combine them. So that's kind of the nice idea there about, with using the box method. So anyways, I go ahead and get this answer, right? So 4x cubed, and I'm assuming since I didn't make any mistakes, that is correct. I need like arithmetic, kind of mistakes. But the problem is, again, this leading coefficient of 2. So what do we do? Like, how do we go from a coefficient of 4 to a coefficient of 2? And again, we got to be careful. We can't like subtract or add a number. That's actually going to be, remember, that would be like applying a transformation. That's going to change our zeros. However, we can change a scalar. Like if we multiply this by 1/2, now you could multiply everything times, actually distribute this all the way through. But since 27 is not divisible by 2, you're going to have a fraction and it's not going to like look as nice. So I'm just going to write the 1/2 out in front because 1/2 times 4 would give me 2, which give me a leading coefficient of 2, which is exactly what I want. But the important thing that I kind of mentioned going back to that original problem here is, when you're writing the zeros, you're writing the factors, you're multiplying out, remember, you could have any number there, right? And again, like here's the important point that I want. Like here is my product of my two factors. If I just wanted to sneak in like the 1/2, you could just throw it in, not there. You could just sneak that in right here, right? Now, obviously, like it doesn't matter. It's just a scalar. Okay, and by providing that as a scalar, you're going to get a leading coefficient of 2. And I'll work through another example I gave my students that will do a problem like that. All right, in the next one, again, we have the zeros, 0, -3, and 3. Set them equal to zeros. Write them as a product of linear factors. In this case, you don't really need to do this. I just wanted to do it, subtract a 0 on both sides so that you can see when you see x cubed, that is written as a linear factor of a 0 of 0 with a multiplicity of 3. You distribute that, you get x to the 5th minus 9x cubed. Now it says it has to contain the point -1, 2. So using function notation, I plug in -1, but when I plug in -1, I get 8. So again, what we need to understand here is how can I write this problem so that it works? And I'm actually going to do this again. I'm going to add on to this. So what I want to do in this case is write f of x equals x to the 5th minus 9x cubed. And what we're going to want to do, though, is use a k here, because that's exactly what I'm trying to figure out. Again, I need to figure out some scalar, right? It doesn't matter what that number is. It could be 2, it could be 3, it could be 5, it could be a fraction. Like, what is the number that I can multiply, though, that's going to make this equal to, when I plug in -1, I need it to equal 2, not, 8. So I use k as this scalar, this unknown number. And so therefore, when I say 2, because f of -1 is equal to 2, so I replace, instead of saying f of -1, I'm going to replace that with 2. When I plug in -1, obviously I get 8. And then I have this k here. So then I divide by 8 on both sides. I get 2 over 8, which is 1/4. So k is equal to 1/4. So therefore, the correct equation, which is right here, f of x equals 1/4 x to the 5th minus 9x to the 4th, which again, you could distribute this. Let's do that. X to the 5th minus 9/4 x cubed. Okay, or you could write the equation, like that. But again, it's important we have to have that scalar. That scalar, again, like when you have that factored out, that doesn't change the zeros, right? But it does change the shape of the graph by vertical actual compression to make sure it satisfies the point -1, 2. Okay, so now let's go and get into the examples that I gave my students here for writing the equation of the polynomial. So very kind of similar to what I did, just here's just some multiplying out, and then we get into ones that have those conditions again. So let's go and get into these examples. Here we have the zeros x equals -1 multiplicity 2, and x equals 2/3 with the multiplicity of 2 as well. Not so fun. Just joking. So we'll say x equals -1. And then x equal to 2/3. Again, I do not want to subtract to -2/3 or subtract 2/3 over because I do not want to be doing multiplication with a fraction. So I can write this as x plus 1 equals 0. And then if I multiply the 3 and subtract it, I should get a 3x minus 2 equals 0. So those are going to be my factors. So I'll write f of x is equal to x plus 1. Don't forget the multiplicity, which is a 2. And don't forget this one has a multiplicity of 2 as well. Now, since I know that the majority of this multiplication is going to be, let's just multiply this out real quick. So again, just remember x plus 1 squared is x plus 1 times x plus 1. 3x minus 2 squared is 3x minus 2 times 3x minus 2, right? So make sure you, again, just apply that distributive property. Do not do x squared plus 1 and, 9x squared, plus 4. Make sure you apply distributive property. Hopefully you can do this, on a separate sheet of paper if you can't do it in your head, because I'm going to get x squared plus 2x plus 1, because since we already practiced the binomial multiplying out, this should give me a 9x squared. Let's see, that's going to be -6x. This will be a -6x, so that's going to be a -12x, and then plus 4. All right, because really the fun part is going to be multiplying the trinomial times the trinomial, which again, I'm going to use my lovely box method for. So I'm just going to create a nice little box, do 3 rows and 3 columns. All right, so I have an x squared, 2x, and a 1. Let's put the 9x squared up here, minus 12x, plus 4. Okay, and again, you could do distributive property, but I just kind of prefer this method here. So this is 9x to the 4th. Now we're just doing length and width for each one. This is a -12x cubed. This would give me a 4x squared. This would be a 18x to the 5th, to the 3rd. Where was I getting to? Oh, I was looking at the... Yeah, be careful with that. I did that actually in class. One of the times I was multiplying 2x times that, but you look at that 9 there, so that's still run. Just be careful with this. I mean, it's a lot of opportunities to make mistakes. That is one of the other reasons, though, why I like using this method is because you can easily kind of quickly go back and check your work and not get, again, even more confused when you're checking your work. Like you can make sure go back and check the length and width of any box, right? Length and width to make sure that you multiply them correctly. And also you can recognize that those all have the diagonal. As long as they're in standard form, those should be in the same, should be like terms. And then now I'm just going to write down the boxes combined. So 9x to the 4th. This is a -12 plus 18, so that's going to be a positive 6x cubed. That's going to be a -20, and then 9, so that's going to be a negative 11x squared, -4x, plus 4. Okay. All right, into the next one here. 0. So again, we're going to have x is equal to x equal to 0. Then we have x is equal to 1, x is equal to -1, and again, another fraction, 3/2. So you could write this as x minus 0 equals 0, x minus 1 equals 0, x plus 1 equals 0, and then x in this case, instead of, again, not doing x minus 3/2, I'm going to multiply the 2 and then subtract the 3. So now I'll write this in my factored form. Is going to be an x minus 0 raised to the 4th power. Then I have an x minus 1 times an x plus 1, and then times a 2x minus 3. So even though this one looks a little bit more complicated, it's actually not going to be as bad because one, obviously x minus 0 to the 4th power can just be written as x to the 4th. X minus 1 times x plus 1 hopefully you recognize is a difference of 2 squares. And then I just need to multiply this 2x minus 3. So I'm going to multiply these two binomials first. Okay, and just using distributive property, I'm just going to do it in my head. You know, I have x squared times 2x is a 2x cubed. Obviously, make the first mistake on the first one. Good job. X squared times negative 3 is a negative 3x squared. Negative 1 times 2x is a negative 2x. Negative 1 times negative 3 is a positive 3. So let's just combine like terms before I distribute that. So negative 2x cubed. Oh, actually, there are no like terms. So let's distribute that x to the 4th now. So therefore, this is a 2x to the 7th minus a 3x to the 6th minus a 2x to the 5th plus a 3x to the 4th. There you go. Nice. Voila. All right, so the next two is going with that same idea in this case. The only thing is now we're going to have these. Again, we need a leading coefficient of negative 4. And in this case, we're going to need it to cover the 0.05. But the first thing we're going to want to do is obviously write the equation, and then we'll deal with the condition. So hopefully you kind of have figured out the writing the equation, and maybe you can do this a little bit quicker. Like this is x minus 3, right? If that's 0, 3, then we know it's going to be x minus 3 squared. These would multiply to give you a x plus or minus 2, so therefore it could be x plus or minus 4. Oh no, minus 4, sorry. So that'd be x plus 2, x minus 2. When you multiply those, that gives you x squared minus 4. So I'm just skipping some steps because obviously the main important point that I want to make with this is going to be obviously dealing with this leading coefficient of negative 4. And again, that becomes x minus 2 times x plus 2. That's where I got that, just real quick. All right, so let's multiply the f of x here. That's going to give us a x squared minus 6x plus 9 times an x squared minus 4. Let's use the distributive property in this case. Let's just multiply everything out. So x, so now I'm just going to do a distributive property. So x squared times x squared is x to the 4th. X squared times negative 4 is a negative 4x squared. Negative 6x times x squared is a negative 6x cubed. Negative 6x times negative 4 is going to be a positive 24x. 9 times x squared is a positive 9x squared. And 9 times 4 is a negative 36. Okay, so now we're just going to combine like terms. Nice, I didn't have to do the box. Like, if you're good at this method, that's fine. Actually, I need to do the cubed first. Combine my x's, x squareds, I'm sorry. Should I have? No, I shouldn't. Okay, so the x squared is the only one, so that's going to be positive 5x squared plus 24x minus 36. Okay? Now, the important thing is, again, there's my polynomial multiply out, but I need it to be a leading coefficient of negative 4. Right? Again, like this negative 4 could have happened anywhere. Like I could have plugged in the negative 4 anywhere I wanted to. I could have plugged in a negative 4 like here. Negative 4 times x minus 3, squared, times x squared minus 4. Like that does not change the factors, right? If I said find the zeros from this case, you would have divided out a negative 4 anyways. Like the negative 4 does not impact this polynomial. So all I need to do is just multiply everything. So basically what I'm going to do is I'm going to take this problem and multiply it by negative 4. Now you could leave it like that as a product of negative 4, right? Or in this case, I'm actually just going to simplify it out. So let's say we got negative 4, x to the 4th. That would be a positive 24x cubed, a minus 20x squared. That's going to be 48, so that'd be a negative 96x. That's 72, so that'd be 144. So that'd be a positive 144. Okay. Now again, first thing you're doing if you were to solve this, you would factor out the negative 4, and then again, that this is just again producing a scalar as well as a reflection, but it's not changing the x-intercepts. All right. So for the next one, I can quickly kind of write the zeros here as an x plus 1. No, x minus 1. So x minus 1 times x plus 2 times an x plus 3 times an x minus 4. Okay, doesn't really matter which ones you want to multiply first. Let's just multiply, these two and then these two. So therefore, in this case, if I was to multiply this, I'd get an x squared plus x minus 2. In this case, I would get a x squared plus 3 minus x minus 12. All right, now we're going to multiply trinomial times a trinomial. And so I'll show you a different method. You can multiply everything out this way. You could also multiply out using the vertical method. So this is a way, you don't want to use an equal sign here, but what you can kind of do is, I'll actually do a different color. You could kind of do like some scratch work. When you multiply like this, what I'm doing is I'm just going to do distributive property. So in this case, I'll get an x to the 4th minus an x cubed minus a 12x squared. Okay? Then I'm going to add that. Oh, I'm sorry. Well, yeah, add that to the next row, to the next derivative. So x times x squared is going to be a positive x cubed. X times negative x is a positive x squared. And x times negative 12 is going to be a negative 12x. And then you're going to add that again to my final result here to be negative 2. So negative 2 times x is a negative 2x squared. Negative 2 times x is going to be a positive 2x. And negative 2 times negative 12 is going to be a positive 24. And the nice thing about this, and this is the way we typically will teach in Algebra 2, we don't really write this plus, but I just want you guys to see. So you multiply the product of each one, you give a row, and now you can just vertically align. So a lot of times if you're having trouble like adding, combining like terms, you can use this method to help you out. And so typically it's not required, a lot of students hopefully won't need that for the pre-calculus, but if you're in a different class, this might be a great opportunity to be able to use. But typically I would like to either use box method or go in there. But this is a great way to avoid mistakes. And if you're like me, you make a lot of little mistakes here. So therefore, this is a great way to avoid those. So negative x cubed plus x cubed is obviously a 0x cubed, which is just going to be 0. Let's see, this is going to be a negative 11, so that's a negative 13 x squared. This becomes a negative 10x and then plus 24. Okay? So that's going to be equal to that. So therefore, my polynomial now, f of x, is equal to x to the 4th minus 13x squared minus 10x plus 24. Okay? Now, the point that we need this to matter to get into is f of 0 equals 5. So when I plug in f of 0, let's figure out what that is. F of 0 is going to make each and every one of these terms equal to 0. Hopefully you guys recognize that. But if you recall, so we have f of 0 equals 24. That does not equal 5. So what we're going to do is we're going to say, well, we need this to equal, we want f of 0 to equal 5. So what I'm going to do is I'm going to say f of 0 needs to equal some scalar k to be some scalar k. So therefore, f of 0 equals 5 is equal to some scalar k times 24, divide by 24, divide by 24, k equals the scalar 5 over 24. I'm not going to want to multiply that out times everything, but so I'll just write it in the front. F of x equals the scalar 5/24 times the polynomial x to the 4th minus 13x squared minus 10x plus 24. Okay, so again, really just understanding the process of writing the polynomials, guys, is really just working ourselves backwards, right? Writing the zeros, writing those factors, and multiplying them. And then also just understanding when we have conditions to recognize that's those are scalars. So they can't impact the zeros. So we're going to use them as values that we would multiply by. And if it's just as simple as a leading coefficient, then you just write that, write a number in front. However, if it's a point, then we need to go ahead and set up that equation to be able to solve for the scalar k. And last but not least, just want to, I ask my students, write down some things that they feel like they understood from the lesson, as well as things that you feel like you had a hard time. And if you want to add your reflection down in the comments below, I'll be more than happy to see how many I can respond to and help you out. Otherwise, hope you guys have a great rest of your day. And thanks for watching, and I'll see you guys in the next video. Cheers.